Iodine is an element with a bluish-black color, and it's a member of the halogen family. Other common members in the halogen family are fluorine, chlorine, and bromine. In higher animals like humans, iodine plays an essential role and it's needed to make thyroid hormones. These hormones are extremely important because they control the metabolic rate of the organism, and if there's an iodine deficiency, this can be pretty detrimental. In the medical field, it plays a pretty important role as a disinfectant, and this is actually where we're going to extract it from. Elemental iodine is a pretty useful chemical reagent, and I'm going to be using it mostly to make something called methyl iodide. Methyl iodide is a pretty useful reagent itself to add methyl groups onto other molecules. Right now, I honestly don't have a huge use for methyl iodide, but I still think it's interesting to make. I also might use the iodine to carry out something called a Grignard reaction. I've mentioned before a molecule that I want to make which actually attracts biting insects, and in the paper that I'm reading, it uses iodine to prepare the Grignard reagent. I might not follow the procedure exactly, but if I do, I will end up using iodine for that. Anyway, now to get more into the details of the actual experiment we're going to be doing. In many pharmacies, iodine can be found in the form of iodine-povidone solution or iodine tincture. This video is going to focus on the extraction of the iodine from the iodine-povidone solution, and I might explore the iodine tincture one in the future, but I'm not sure. Before we start off though, let me just say that it's a pretty costly method to get elemental iodine, and it's much cheaper to just buy it directly. These are the main ingredients that I used for this experiment. I made a mistake and I forgot to include hydrochloric acid in this shot, so we're going to have to just pretend that it's there. I used 500 milliliters of 10% iodine-povidone solution, but the amounts of the other reagents doesn't have to be really exact. I would make sure to have at least 100 grams of sodium hydroxide, 500 milliliters of 3% hydrogen peroxide, and about 150 milliliters of around 31.45% hydrochloric acid. The first thing that I do is I prepare a sodium hydroxide solution. With stirring, I added about 30 grams of sodium hydroxide to roughly 75 milliliters of water. It actually turned out that I used twice this amount of solution, so instead I would actually use 60 grams of sodium hydroxide in about 150 milliliters of water. As the sodium hydroxide dissolves, it will produce a lot of heat and the water will get pretty hot. It was stirred until everything was dissolved and it was somewhat clear, and then it was placed to the side. To a 1 liter beaker, I poured in the 500 milliliters of my 10% iodine-povidone solution. The solution is extremely dark red, and as you pour it, a little bit of bubbling occurs. Once everything's been added, I use my magnetic stirrer to start mixing it. A magnetic stirrer is not mandatory, it just makes things easier. If you don't have one, you can also stir it with something like a glass rod. So now with strong stirring, I start to add the sodium hydroxide solution that we made before. You can see that after it's added, some solid stuff is floating around. In this shot, I'm adding the sodium hydroxide solution that I originally made, which used 30 grams. However, even though I calculated this to be enough, it didn't seem to be. This is why I said you should have at least something like 100 grams on hand, just in case you need to make more sodium hydroxide solution. So that's what I ended up doing, and I dissolved 30 grams of sodium hydroxide in another 75 milliliters. As I continue to add it more, it's going to take on more and more of a yellow color. This color change is extremely important because this is what lets us know when we've added enough sodium hydroxide. Iodine is really not very soluble in water, and this is why povidone is used. The povidone is a water-soluble polymer that will actually form a complex with the iodine and allow it to stay in solution. This way, you can get concentrations of iodine that are much higher than if you were to try to dissolve iodine alone. By adding sodium hydroxide, our goal is to react it with the iodine and convert it to sodium iodide. I'm not exactly sure what the reaction between the sodium hydroxide and the povidone is, but it makes it much less water-soluble and causes it to precipitate. When the stirring's turned off, the povidone polymer stuff will float to the top and we're left with a yellow solution. After letting it stand for a bit, you'll notice the stuff at the top is no longer orange and it's also yellow. This yellow color serves as our endpoint to tell us that we've added enough sodium hydroxide. The iodine is strongly colored, but when it's in its salt form, sodium iodide, it's colorless. So when the red color and orange color are gone, and we're left with just this yellow color, we know that we've converted pretty much all of our iodine into sodium iodide. The next step is to filter off this polymer that's just floating around, and to do this we use coffee filters. Because we're working with a strong basic solution, I would recommend using 2 coffee filters because the base might destroy one and then everything could fall through. As it filters through, you should notice that the solution we're getting is colorless. Once pretty much all of the top layer of the polymer has been removed and most of the water is filtered through, I added a little bit of water to wash it. We still need to filter through the rest of the solution, but to do this through the polymer would take a while, so I set up a separate filter. The coffee filters here were also doubled, and we filter it just like before. It took a little while, and everything slowly filtered through. As the water filtered through and hit the surface, it made a weird effect. I'm not really sure what the exact reason is for this. After everything had filtered through in the second filter, I added a little bit of water to wash the polymer. The water slowly trickled through, and what was cool is it formed a little bit of a layer on the top. The density of our solution is much higher because it has a lot of stuff dissolved in it, and so the distilled water, when it slowly drips in, it just floats on the top. In the meantime, while it was filtering, I cleaned my 1-liter beaker, and now we'll use it again and we pour both of the filtered solutions in. At the bottom of the beakers, there might still be a little bit of polymer goo, and don't include this when you pour your stuff in. You might notice that the volume is a little bit higher here, and this is because of the water washings that I did. Now what we're going to do is we're going to boil down the solution to reduce the volume. This will do 2 things for us. It will concentrate our sodium iodide solution, but also the reduced volume will cause the rest of the polymer to precipitate. As we boil it down, the solution actually starts to clear up a little bit, and we're left with a large chunk of polymer floating on the top. The volume was reduced to about 250 milliliters, and then it was removed from heat. Now again, we will repeat our filtering step. This time, it should be much faster to filter everything through. When everything from the beaker is added, I put a little bit of distilled water into the beaker to wash it a little, and this is poured through the filter. When the washing hits the solution below, it gets a little bit cloudy because the water washing was done with cold water, but the water below is hot. The solubility of a lot of things is much less in cold water, so when it hits the hot water, it causes some things to precipitate out. I had to remove my stir bar from the polymer, and as you can see, it's pretty gooey. It's really not very sticky though, and its texture reminded me a lot of silly putty. As long as the polymer was wet and hot, it was extremely malleable. Like I said, the consistency was almost exactly like silly putty, and I couldn't resist playing with it a little. I decided to be really cool and make the initials for my channel, so I made an N and an R. It only took me about 30 seconds, and here you can see my really crappy creation. Here's an up-close shot of my beautifully crafted letters. Anyway, now we can get back to the actual experiment. The next thing we need to do is again concentrate the solution by boiling it down. So just like before, we put it on a hot plate, and with some strong stirring we boil it. The goal is to boil it down until it's pretty much around 50 milliliters. You might notice that there's a little bit of yellow polymer floating around. This is remedied pretty easily, and I just take it out using a spatula. Before proceeding on, I highly recommend you let it cool down all the way to room temperature. The next step is to add hydrochloric acid, and the reaction can be pretty exothermic. You can see here I didn't let it cool enough, and when I pour some acid in, a lot of splashing occurs. That little experience taught me a lesson, and I decided to let it cool down all the way to room temperature before adding more. Even at room temperature though, you can see that the reaction is still pretty exothermic. The reason for this is that we have a pretty concentrated solution of sodium hydroxide, and neutralizing it with hydrochloric acid produces a lot of heat. You might notice that where the hydrochloric acid is added and reacts, it produces an orangey yellow color. What's happening here is actually several different separate reactions. Like I said before, we do have an acid-base reaction going on between the hydrochloric acid and the sodium hydroxide. This will be the major reaction that occurs because until all the sodium hydroxide is consumed, we won't have any hydrochloric acid to take part in the other reactions. Once the sodium hydroxide is being consumed, we start using the hydrochloric acid in two other separate reactions. The reaction we did earlier between povidone and sodium hydroxide produces sodium iodide and sodium iodate. Both of these will react with hydrochloric acid to produce sodium chloride, iodine, and water. More sodium iodide is present than sodium iodate, so eventually all of the sodium iodate is consumed. The I2 that's produced in this reaction will complex with sodium iodide to form sodium triiodide. This complex is water soluble and has a faint yellow color, and you can see it forming when some of the hydrochloric acid is added. The final thing that's occurring to some degree is some of the sodium iodide will react with the hydrochloric acid to produce small amounts of hydriodic acid. Hydriodic acid is a stronger acid than hydrochloric acid, so the formation of a stronger acid from a weaker one is not very favored at all. It's an equilibrium reaction where the products aren't very favored, so the amount of hydriodic acid that's produced is going to be very small to almost insignificant. When we combine all these reactions together, we're left with mostly a solution of sodium triiodide and sodium chloride. Sodium iodide has a much higher solubility in water than sodium chloride, so it should be mostly the sodium chloride that precipitates out. As the solution started to heat up again as more hydrochloric acid was added, the splashing got worse. To remedy this, I simply just put a watch glass on top to block anything that might have splashed out. Of course, we could go the route of actually cooling everything in an ice bath and then adding everything slowly, but I didn't really want to do this. The amount of hydrochloric acid here will depend entirely on the concentration of the iodine-povidone solution you used and how much sodium hydroxide you used in the beginning. In the end, I don't remember exactly how much I added, but it was in between around 100 to 150 milliliters. The solution is white, but as more is added, there'll be a point where the solution becomes yellow. When the solution becomes yellow, this is our end point. Once it reaches this point, I add more hydrochloric acid to make sure there's an excess. If you do this reaction, you also might get a brown colored solution, and this is also okay. More dilute triiodide solutions are yellow, but the higher concentration is brown. After the reaction with the hydrochloric acid, there was a lot of precipitate which needed to be filtered off. The precipitate is likely just a lot of sodium chloride produced in the neutralization. This can be avoided if you limit how much sodium hydroxide you use in the beginning. There's really not too much harm in adding too much though, because the worst that can happen is you use more hydrochloric acid and you have to do this filtering step. Anyway, once we filtered it, we're left with a nice clear yellow solution. To a 1 liter beaker, I added 500 milliliters of 3% hydrogen peroxide. The goal in this step is to use the peroxide to oxidize our sodium iodide to the elemental iodine. To do this, it's very simple, and we just pour in the hydriodic acid solution to the beaker. Immediately once it's added, it takes on a very dark red color, but then it starts to get cloudy. This cloudiness is due to elemental iodine being produced and precipitating out. I let it sit for a bit, the solution totally cleared and all of the iodine sank to the bottom. I then decanted the upper aqueous layer. This iodine was then vacuum filtered off. I opted to vacuum filter it, but it's just as viable to gravity filter it using something like a coffee filter. After everything was filtered, the iodine was washed with a little bit of water, and the vacuum was kept on to dry the iodine a little. Once the iodine was relatively dry, it was scraped off into a beaker. In this step, we're going to purify the iodine by evaporation. I think the fact that I didn't use the term sublimation might actually shock some of you. Well, I didn't use the term sublimation because actually technically the iodine isn't going to be sublimated. The definition of sublimation is the transition between solid and gas phase without going through a liquid phase. Before I start with my explanation though, I want to be very clear and state that it is true that iodine does sublimate at room temperature. However, what we're doing here is we're heating the iodine, which is different than letting it just sit at room temperature. When the iodine is heated, it does become a vapor, but first it actually does pass through a liquid phase. There's actually a really large window between about 113 and 184 degrees Celsius that it exists as a liquid. So if we heat iodine, we can't say it's being sublimated because it's not going directly from solid to vapor, it's going solid, liquid, and then vapor, so it's more being evaporated. After doing a little bit of research, I found that it's a pretty common belief that iodine cannot be a liquid at atmospheric pressure. I'm going to be totally honest and say that I was one of these people who was always taught this. When carrying out this purification step, though, I did notice that the iodine was liquefied, and that really made me question what I had learned. The first step in this process is to place a flask of cold water on top. We can then start to heat the beaker, and you'll see a lot of vapor coming off. As we continue to heat it more, the color will get stronger and stronger. Now this here is the interesting part, which I didn't expect because like I said, I was always taught that iodine only sublimated. If you look at the walls of the beaker, you'll see a line climbing up the side. This is actually the vapor front of liquid iodine. As we keep heating, you'll see that it climbs higher and higher up the walls. Just to show you why we use the flask, when it's removed, purple vapor comes out. Eventually though, it will reach a height where it becomes very evident that there's a liquid recondensing. This isn't water or some other solvent that I didn't separate, this is actually liquid iodine. When we feel like enough crystals have settled on the side of the beaker, we take it off heat and let it cool down. Once it cools, you notice that all of the purple stuff on the side of the beaker is now gone. So now it's time to harvest the crystals, and the first thing we do is we take off the flask and scrape off the crystals that might have collected on it. Whenever I carry out these quote-unquote sublimations, I never get any crystals settling on the bottom of the flask. For me, it always settles on the side of the beaker, but if you were to carry this out, you might get a lot of crystals on the bottom of your flask and not so many in the beaker. Anyway, once the flask is clean, we can move on to scraping the crystals out of the beaker. We're only interested with what's collected on the side of the beaker, and we don't touch anything that's at the bottom. The iodine on the side of the beaker should be nearly pure, whereas the stuff that remains at the bottom is going to be pretty dirty. So everything I've scraped off the walls, I dump onto the piece of paper. So here you can see we're starting to get a little bit of a pile going. Now there still is iodine at the bottom, so we carry out this process again. So it's the same thing as before, we heat it until there's a large amount of iodine vapors in the beaker, and then we take it off the hot plate and let it cool. As it cools, iodine crystals will form on the side of the beaker. So once it's cooled down, this is what it looks like. We can then start the same process of scraping the crystals off the bottom of the flask, and then taking them out of the beaker. This second process is going to yield a lot less iodine, but it's still worth doing. After all the iodine scraped off the walls, I add it to the rest. I place on a watch glass the final yield of iodine. The final amount that I collected was around 2 grams. I transferred what I got to the bottle which contained all of the other iodine that I already have. At room temperature, iodine does sublimate, and this is why I have a plastic bag around the bottle. It just means that if any iodine vapor escapes the bottle, then it will be trapped in the bag. So now a little bit of some extra stuff that turned out to be pretty interesting. To clean out the iodine, I use a crazy excess of sodium thiosulfate. I stated earlier that iodine is really insoluble in water, so this poses a little bit of a problem for cleaning. We could in theory do like we did at the beginning of the video and react it with some sodium hydroxide, but I find that using something like sodium thiosulfate, which is much more mild, is more to my taste. In either case, we're converting the iodine back into sodium iodide, which is colorless and water soluble. So I use this concentrated sodium thiosulfate solution to wash out all of my beakers, and it works very well. I pour some into the filter that I use that still had some iodine on it, and you can see immediately the purple color disappears. Now for the interesting part that I totally didn't expect, but I probably should have. I added sodium thiosulfate to the hydrogen peroxide solution that we filtered the iodine out of. When this happens, the color immediately disappears and it becomes clear again. I'm not sure why, but the solution that originally we filtered the iodine out of was pretty clear, but after letting it sit out for something like a day, it became dark and reddish like you see here. Anyway, the cool part is that it quickly goes back to the red color. I was actually able to add the thiosulfate solution several times, have it convert back to colorless, and then let it sit and it would slowly become colored again. I said that I didn't expect this to happen and that I probably should have because I coincidentally made a pseudo-iodine clock reaction. There are a few ways to make the iodine clock reaction, and in this case, this is the hydrogen peroxide variation and the only thing missing is starch. I thought that this was just an interesting coincidence that I happened to use sodium thiosulfate, and I thought that you guys might find this interesting. Again, here's a list of the videos that I'm currently editing and future videos I plan to film. In the videos being edited category, you can vote for the one that you want me to publish next, and in the future video category, you can vote for the one that you want me to film next. Also, if you're feeling generous, please donate to my Patreon account because with a bigger budget per video, I can do more things. Also, instead of stockpiling videos, I've decided I'm going to publish them as soon as I edit them, so in the next month or so, there's going to be a lot of videos coming out. On my Patreon, I also added a milestone, and if we get to $250 per video, I'll commit to doing videos for at least 6 months.